At 4:45 on Friday, a new syslog and SNMP management server is ready to go live. The change sounds small. Point every router and switch at 2 new IP addresses, then save. On 5 devices, that is routine. On 500, 1 typo, 1 missed device, or 1 unsaved configuration becomes a weekend troubleshooting incident. The right decision is not to type faster. Use software to apply the same tested change consistently, report failures, and leave people free to validate the design. That is network automation, a range from small scripts to platforms coordinating many dependent changes. Its big win is lower operating expense, or OpEx, fewer labor hours, faster deployment, and fewer repetitive mistakes. It does not lower capital expense, or CapEx. Automation does not remove the need to buy network hardware. To diagnose the incident, separate each device into 3 logical planes. The data plane, also called the forwarding plane, moves frames and packets using rules already in place. A switch forwards based on its MAC table, a router forwards based on its routing table. The control plane creates or updates those rules. OSPF builds route information. STP decides forwarding ports, and ARP supplies IP to MAC mappings. The management plane is how we configure, observe, and maintain the device. SSH, syslog, SNMP, and NTP belong here. A management plane change can affect control plane behavior, which then affects forwarding, but the roles stay distinct. In a traditional routed network, every router runs its own control plane processes. Each router exchanges routing information with neighbors and independently calculates routes. That is a distributed control plane. Intelligence is spread among devices. It can work very well, but large-scale policy changes mean translating intent into many device-level configurations. For our syslog change, the engineer still has to reach every device, even if a script reduces the effort. The operational question becomes, can we express the desired outcome once and have a system consistently translate it across the network? Software-defined networking, or SDN, moves some or all control plane intelligence into one or more controllers with a broader network view. Applications send requirements to the controller. The controller calculates policy and distributes instructions. Important correction: SDN does not centralize the data plane. Routers and switches still forward traffic locally and at line rate. What changes is where control decisions are coordinated. This controller-based model makes programmatic, repeatable changes practical, while preserving distributed packet forwarding in the infrastructure. Think of SDN as 3 layers. The application layer states a desired behavior, such as isolating guests or prioritizing video meetings. The control layer turns that requirement into device-level policy and forwarding instructions. The infrastructure layer is the switches, routers, and other devices that enforce them. Between application and control is the northbound interface, or NBI. It commonly uses REST APIs over HTTP. Between control and infrastructure is the southbound interface, or SBI. The SBI can use OpenFlow, NetConf, OpFlex, or established management protocols such as SSH and SNMP. Northbound is application to controller. Southbound is controller to devices. Cisco applies these ideas in several domains. SD Access automates wired and wireless campus networks with Cisco Catalyst Center, formerly DNA Center, as controller. SD-WAN builds an overlay of IPsec tunnels across available WAN transports, such as Internet, MPLS, cellular, or satellite, with controllers for onboarding, control, and management roles. ACI is Cisco's data center solution. Its APIC translates policy across a spine leaf environment. In each case, the underlay is the physical transport network. The overlay is the virtual tunnel network built across it. The fabric is the combined physical and virtual system. SD Access and ACI commonly use VXLAN overlays. SD-WAN commonly uses IPsec overlays. Now, return to the business problem. Instead of writing QoS commands on individual switches, an engineer can state an intent. Video conferencing must receive priority over less time-sensitive traffic. Intent-based networking lets the controller translate that outcome into the required policies and configurations, deploy them consistently, and help verify the intended state. It does not mean the engineer stops thinking. The engineer owns the policy, scope, validation, and rollback decision. The controller owns repetitive translation and distribution. That shift, from telling every device how to behave to declaring the outcome, builds on automation and SDN. AI is the broad field of systems that analyze information, identify patterns, and make predictions or take actions. Machine learning, or ML, is a subset of AI that learns from data rather than relying only on explicitly coded rules. Supervised learning trains from examples paired with known answers. Unsupervised learning finds clusters or structure in data with no supplied answers. Reinforcement learning improves through interaction and positive or negative feedback. Deep learning is a further subset of ML, using multi-layer artificial neural networks. It can extract more complex patterns from large datasets, including unstructured data. These approaches can help operations teams find behavior that is too large or subtle to notice manually. Predictive AI uses historical and current data to forecast what may happen next. In operations, that can mean traffic forecasting before congestion, maintenance before a component failure, capacity planning, or identifying patterns associated with threats. Cisco Catalyst Center provides concrete examples. AI endpoint analytics can identify and classify endpoints for policy. AI-enhanced radio resource management uses past RF data to recommend wireless settings. And its machine reasoning capability supports root cause analysis and possible corrective actions. Edwards, Clayches, Aromani, Sykinchens. Generative AI creates new content, a draft automation script, documentation, a network diagram, a configuration template, or a design proposal. Treat predictive output as a forecast to validate, and generative output as a draft to review and test. Neither removes accountability. The syslog rollout succeeds when the intended configuration reaches every in-scope device, failures are visible, and monitoring confirms the new server receives events. The lesson is larger than one script. Automation cuts repetitive operating work, not hardware cost. Data planes forward, control planes decide, and management planes configure and observe. Traditional networks distribute control decisions. SDN coordinates control through controllers, while forwarding stays distributed. Applications use northbound REST APIs, controllers use southbound protocols, and overlays ride over physical underlays to form a fabric. Finally, ML and AI can forecast, explain, and draft, but engineers still decide what is safe to deploy. That is the practical path from CLI firefighting to reliable network operations.